This conference will now be recorded.
Hi, good morning. Hope you're able to hear me well. Actually, I can see only two people who have joined. Please confirm if you're able to hear me well and also are able to see the screen. Can you please confirm?
Yes, Madhu, we are.
Okay. Okay, fine. I think only two of you are there right now, but let's get going. Did you receive the .ipynb file that I have sent you for the first lesson of our second project?
Yes, Madhu, we received.
Okay, and you were able to kind of use that code and up to date now, whatever exploratory analysis of basic information from the data set you were able to complete. Am I right?
Yes, till DF types and all.
Okay, fine. So now from that onwards, we'll move forward. Okay, so just to quick recap where we are doing the second project, and our second project is not a toy project. Second project, we got a data set, decent data set with some 1883 observations of various properties that have been sold, and we captured some 25 characteristics of the property and one column, that is the transaction price, that is the target variable. So using that kind of data set, we want to build a professional grade prediction model to predict the fair transaction price of the property. Okay, so in case the firm that gave this project to us, if they want to predict for new properties, they can give all the characteristics, type in them in an application, and then instead of having to depend on a human real estate appraiser, they can depend on our data driven solution, which we are promising to the client that which will do better than your unskilled or inexperienced real estate appraiser. That is what we have set a goal for ourselves as we started the project. And then I introduced you to the process, 5-step process, which again will be subdivided into 5 sub steps. So a 25-step template that we are going to use as we build this project. And I told you every machine learning prediction model building project can follow the 25-step template. So carefully register in your minds all the steps, and within those steps what we are doing. So if you perfect that process, then the problem that will be solved will be different every time, but at least you can do some things pretty fast and pretty well. That is the goal. So we are in our first step of our project, that is exploratory data analysis. So as I told you in the previous session, exploratory data analysis is about like your first date with your data set. You will spend some time to get to know about the data. So that step, I told you, it's a little bit open-ended kind of step, because if we don't have some goals in our mind, simply start doing about it, then we might get lost and we may not achieve our purpose of learning the data so that we can do the next steps of data cleaning and feature engineering in a good manner. That is why we thought we will use a template. In our template, we told we'll first spend some time exploring the basic information that is available in the data. After having done that, we will do focus only on the numeric features, and we try to understand using some visualizations as well as some descriptive statistics. We try to understand the distributions of numeric features. Then we will get to know more about any potential outliers, any measurement issues, any sparse classes, any missing information. Again, what is the kind of metrics around standard deviation, interquartile range, all those things we will understand for numeric features. After having done that, we want to spend some time focusing only on the categorical features. Again, categorical features are the columns where the columns are filled with some descriptions, not numbers. That kind of columns we call them as categorical features. Then after having done categorical features in a focused manner, then we will use categorical features side by side with their numeric columns and try to understand them. Then find any potential other issues by seeing them together, categorical alongside their numerical, other numerical features. So that we call it as segmentations. And at the time of learning pandas, we did these exercises basically using those group by and aggregating the statistics, all those capabilities we'll use to understand the data in a much better way. And after having done that, we will focus on understanding any correlation is there amongst our features, especially the features and the target variable. Correlation is a statistical term. We'll talk about it, but doing correlation analysis. If you put these 5 steps in your mind very clearly when we are talking about exploratory analysis, any new data set, any new project situation, you can very focused manner do this and try to get to know about your data, which is a very important first step. Okay, so already we have done basic information. Today we will do 2 things. We will try to understand the distributions of numeric features in our data set, our real estate data set, as well as distributions of categorical features. These 2 tasks we will do in today's session. So get ready with whenever we get into coding, not much of code will be there, but first we'll understand and then quickly do that. So let us go to the second step, and the second step is distributions of numeric features. Okay, so when we look at distributions in general, either numeric features or categorical features, what we should look for? First, look for some distributions that are unexpected. Are the min, max, and the mean and the standard deviation, and is the min value and max value within the range of are closely related to standard deviation or not? Okay, anything that is unexpected, we have to look for that. Then potential outliers that don't make sense. We talked about outliers previously. We look at mean and median, then we look at standard deviation and try to understand each observation, how far is it from the mean. That indicates actually our standard deviation. Any observation, actually if the standard deviation is more, means some observations are falling very, they are very distributed in a big way from the mean. So those kind of analysis we have done using standard deviation as well as our IQR in that interquartile range. So there is a median and there is a Q1, there is a Q3. So most of the observations should fall between 25th percentile and 75th percentile. So anything falls very far from Q1 and Q2, Q3, we consider them as potentially outliers. So we have to look at that. So again, we'll come to each point, don't worry now. Again, sparse data, any data that is there but it is not prevalent amongst many observations, very less number of those things are there. Especially this is with respect to our categorical data, we'll come to that. Okay, then features that should be binary but recorded as ints or floats. Okay, like for example our basement, right now we see that it has been recorded as a float 64 number, whereas actually our data dictionary is saying that it should be basically it is a binary
Yes, sir.
integer value.
Yeah.
Any question?
No, sir.
Okay. Then boundaries that don't make sense, potential measurement errors, all these potential things we have to observe as we try to observe the distributions among our numeric features as well as our categorical features. Okay. So this how will we do? We will do using both visually. We draw some graphs because we have matplotlib and as well as SNS, okay, Seaborn. Using both of them, we will be able to uh, visualize. We will be able to visualize the information, as well as we can look at our descriptive statistics using our dot describe function, and both will use to understand the data better. Okay. So when we want to look at all the numeric features, a useful visualization is a histogram. Okay, basically a histogram picks the numeric information from a column and it calculates, actually it automatically, without any, if you don't really tell it, it will look at the data and understand the frequency of various numbers occurring in that, and it adjusts what we call in the x-axis bins. Okay, so for example, if you look at this transaction price, so in our data the min value is 200,000 and the max value is 800,000. So it basically looks at the data and creates a particular kind of bin size. So here it has created a bin size of 100,000 in between. So 200,000 to 300,000, 300,000 to 400,000, like that. It has adjusted the bins and it puts how many observations on the y-axis count are falling within that bin. That is how histograms are done, and histograms are useful for understanding distributions exist in numerical data. So basically they tell you the basic distribution. If you look at our at least transaction price, so most of the houses properties are actually between 30,000 and 40,000. So somewhere the mean will lie between them, and it is not a uniform normally distributed data. It is skewed towards the right little bit. So higher value properties are in fewer in number, whereas most of the properties seem to be sold between 300,000 to 400,000. Okay, so it gives you visually, you can look at it and but understand how the data is distributed from its mean. Those kind of understanding we can do, and again we can look at everything and find through the visualization we can think in our mind anything potentially wrong. Let us look at each of them. So if you look at our TX price, seeing this, we can, it's okay, it's not, it's a good data. Okay, but maybe, see, if you look at it, it is very cleanly separated. Minimum is 200,000, maximum is 800,000. Do you think properties have not been sold just below some 200,000 or just above 800,000? Maybe to make the data more appropriate, or for some reason some truncation took place. So anything after 800,000, maybe they have truncated and put it as 800,000 maximum, and maybe anything little less than 200,000, they might have all added into 200,000 bracket. So a clean separation, if you look at like this, at least we'll think about potentially some, the min max are truncated. Okay, that kind of, but otherwise this is a good histogram, nothing else we can think. Let's say here we have lot size. Again, I'm only plotting histogram for lot size. So if you look at it, it has automatically put some bins. So if you look at it, first one is actually 0 to 100,000, and next is 100,000 to 200,000, 200,000 to 300,000, like that. I think the bins have been put as start at 0, and the first bin is at actually 200,000 square feet. Lot size is measured in square feet, so 2 lakh square feet. Okay, most of our observations, 1883 observations, are falling within 0 to 100,000 square feet. 0 to 1 lakh square feet lot size only. Most of the properties are there. A small thin bar is available for actually from 100,000 to little more than 200,000. So some bigger lot sizes also are there. But why actually the histogram has been built with all these other bins? So there may be a problem in the data. There may be one or two observations which are actually somewhere close to 120. This is 1,20,000 square feet plots. Okay, means these are much larger plots than our normally all other plots. Okay, so these are called potential outliers. Maybe uh, this particular county, some New York, we are looking at all the properties. Okay, all these have been sold, and one property that belonged to, let's say, Michael Jackson was also sold, and that had a lot size of 1.2 million square feet. Now we have to ask in our observations, should I keep it or not? Is it an outlier? But we will come to that. That's why we are calling it as potential outliers. But right now, what I am trying to tell you is that when you visualize using histograms for your numerical data, you have to take a pause, look at any unusual things that are you are observing. So this is a little bit unusual thing. Okay, because though it is required two bins, but our histogram actually made a bin up to 1.2 million square feet. So immediately you make a note, there is some issue with lot size. There are unusually bigger lot sizes in our properties. Okay, that we will go and look at it. We will sort values by lot size ascending, then we will see are there any properties which are really large, should we keep them in the data or not. Okay, hope you are with me. Any questions?
Yes, sir. Sir, one question. How can we
Yeah,
differentiate between outliers and sparse data?
that will come to that. Right now we are talking about outliers. We will also talk about sparse later. Okay, outliers are basically, they are some observations which are very far from the standard deviation, or which are not very far from the 75th percentile, or very far from 25th percentile. So these are some unusual observations. Those things are called outliers. Okay, we'll come to sparse soon. Can I
Right,
move
sir. Thank
forward?
you. Thank you, sir.
Okay, fine. So potential outliers. So whenever you see such a histogram where the bars are there for two, but the bins have been made, many bins have been made, means there are, maybe there is a one observation with 1.2 million square feet lot size number data, maybe there in the our 1883 observations. So that gives you visually, then you have to look at statistics and understand, and then take an action. So right now we are in exploratory data analysis. We are getting to know our data and making notes as we are learning about the data. All these notes we'll use when we start cleaning the data. Keep that in mind. Okay, then features that should be binary indicators. Already we observed this basement feature, which is filled with 1.0, and most of the other observations are filled with nan, not a number. Okay, maybe this should not be recorded as a an int 64 or float 64 kind of data type, it should be more of a binary. If basement is there, 1. If basement is not there, 0. That could have been the right way. So there is a problem with our data set, especially with basement. We'll have to correct it. Okay. So that is what we are telling. Then again, we told actually our data is actually up to 2016 transactions. The customer shared with us a data that is up to 2016. But when we do this kind of histogram, immediately from histogram we cannot really know anything. Okay, because here the bins are made with a 20 years kind of bins. Okay, so there is 2000 to 2020 till the end, but this bar we don't know whether it is 2016 or 17 or 18 or 19. What is this end date? We don't know. So sometimes we can't really say with histograms about that. Then we have to go look at for our year built column, what is the min year, max year. Then we will know whether is there any potential measurement error, like do I have a data set with up to only 2016 built year kind of number, or some little bit later. If later, then we have to remove the data. But these are the things. Okay, we have to see these things and then we have to ask questions. So visualizations, seeing a picture, are most useful when they are paired with summary statistics. Okay, together with numbers and pictures, we have to see the data and try to explore and understand and make notes about potential problems with the data. Okay, visualizations help build intuition, like whatever I've shown some examples, and that is the intuition quickly and at a glance, while summary statistics provide more precise information. So together we will use to understand how the numeric columns are distributed. That is what we are doing. Similarly, we have to do it for how categorical columns are kind of distributed. So we know how to get this kind of numbers. If you put df.describe on your df, so it calculates for all columns some basic statistics. First, by default, it calculates for all numerical columns all these values. It counts how many observations are there, what is the mean for that column, what is the standard deviation for the column, what is the min of the column, what is the Q1 or 25th percentile. Already we talked how to calculate of the column, 50th percentile, this is the median of the column, 75th percentile or Q3 of the column, and max value of the column. For every column it calculates. We have actually in our data set we have 26 columns and 1883 rows. When we looked at the shape, out of that, one column, that is our tx underscore price, is our target variable, and rest of the 25 columns are our input features. And in that input features we have 22 numerically recorded features and 3 are object type. They are having some descriptions in those observations, especially the property type, the exterior wall type, and the roof. These are the object types. That's what we have. While we explored the basic information, we came to know. Okay, so now along with our year built, if we want to are interested, then max is actually 2015. Though the histogram did not let me understand what is the max year built, so we have only properties that are built till 2015. Beyond that we don't have. Okay, good to know. Then if you look at this data again, very 200,000 and below that nothing is there, 800,000 after that nothing is there. So most probably they might have truncated some data and added some properties little more than 800,000 all into 800,000, something less than 200,000 all of them to 200,000 they put, and in between they have put the numbers. Okay, at least that you get an idea by seeing this descriptive statistics. Then if you look at the lot size, the mean value, again these are differently scaled. We have to convert them, but the mean is actually somewhere around 133,000, 1,33,000 kind of, not 133,000 or 13,300 kind of thing. Here it is 1.2 million, the max. So there is a potential outlier that we also saw visually, that unnecessarily it created bin size up to 1.2 million. So definitely we have to look at those things. And if you look at this basement here, it's all having same number. Mean is 1.0, standard deviation is 0, because if you look at that column, the column is filled either with 1.0 or nan, and only 1657 columns only are filled. Okay, so lot of missing numbers are there, missing. The column is not properly filled also. Okay, it gives you that kind of information. Okay, so now that is what we will do analysis on our data set now with respect to our second point, that is, let me take few minutes and understand the data by looking at only the numeric features and create few visualizations, and also look at some descriptive statistics and understand the numbers and make little bit of notes that I will use to do my data cleaning. Okay, so anyway, let us do this. uh, how many of you are already having all this? We can move fast because I sent you the IPYNB file up to basic information. So what you have to do right now is that you just run those cells. Okay, so first is header. So we are importing numpy as np, pandas as pd, matplotlib, seaborn, and one thing that we did for this data set is that we did pd.set_option. We want to see all the columns by scrolling horizontally. So that is why we have put this, so that we can see all the information at a time. Then what we did, we are reading our real_estate_data.csv. Wherever you saved, you are reading it to df. So how many of you are at this place? Can I move forward?
Yes, sir.
Okay, so we have our data frame there. Now let us go do little bit of exploration on our numeric data types. So as I told you, we can visualize using histograms for our numeric data. That is one way to understand the distributions, by seeing. So there is a .hist function that we can run on any df. When we do on df, so all numeric columns, it will create one picture like this. Okay, just run this df.hist and plt.show. It may take a little time because it has to calculate for 24, no, 23 columns and create 23 pictures like this. Got it? Okay,
Yes, sir.
can I move forward? Okay, so
Yes,
but
sir.
it is not very good, it doesn't look good, we cannot make sense. That is why if you go to df.hist function, there are a lot of arguments to make your visualizations more clear for you. So you can go and look at the documentation, but two things let us do. We can increase the size of each picture by playing with our one argument called fixed size, and you can give a tuple with these numbers 14 comma 14. If you give 16 comma 16, little bit bigger picture will come. Then there is another argument called xrot, that because we have a whatever x-axis, you have some description for every bin. That bin, if it is vertically drawn, we are not able to read, it is going into the next picture. So what we are doing is that we are putting it as a -45, little bit angle, we are trying to print it. Okay, so that it doesn't come to the next picture, so that all pictures together we can see. So basically here what we are doing really, if you are able to, small picture is, small things are there, but df dot histogram is hist. Okay, and in the first argument I am passing fig size. Fig size, that is the argument name. Okay, again fig size s is small equal to tuple. I am passing 14 comma 14. Okay, that is why there is this parenthesis. Then as a next argument I am passing x, small x rot, x rotation. Okay, so that I am doing it as equal to minus 45. Okay, so minus 45 degrees angle may it will be print. Okay, so that is what I am passing, and again showing it using my plt.show. Then you might have got little bit improved pictures. Did you get it?
Yes, sir.
Okay, so now once you get pictures, you should not be happy. Oh, my pandas worked, some good picture has come. You should not get happiness like that. What you have to do, you have to pause, look at, because sometimes the columns will be many columns. Okay, whatever our data set, it is only having 26 columns. Out of that, 23 are actually the numeric columns. So 23 histograms are done. But maybe in future you will work with a table where you are dealing with some 150 numerical columns. Okay, so anyway you will not spend lot of time doing that. But quickly, is there any uh, unusual things are there? Basement, there is a little bit, only one bar is there. Okay, then we also looked at lot size. Okay, there is one big bar and a very small thin one, and then the bins are there till long to the right side. Those are the unusual things you have to stop and see when you are looking at histograms. Let's say you got a doubt with respect to one column, then you can do a picture for only one your column. So here what I am doing, df dot my column name. Okay, any column, numeric column name. Okay, and on that I am running my histogram function. So I can see only one histogram at a time as well. Okay, so wherever you get doubt, you want a little bit more clean picture and you want to look at it, understand from the picture point of view, you can do this as well. For any of your column, df dot, only you have to type your column name very clearly. For year built, it is year underscore built. So that is my column. On that I am running my hist function without any arguments. Okay, so I can see. So you can see for each of those things. Okay, got it. Can I move forward?
Yes, Madhukar.
Yes, sir.
Okay, so as I told you, with histograms, with these visualizations, we get little bit of idea about our data, but then we have to use numbers alongside. Then only further clarity will emerge about a particular data, how it is organized, what is its distribution and all that. So that is where we know already when we did pandas, there is a very useful simple function, that is df dot describe. Okay, when you do df dot describe, it actually calculates for each of the numerical columns the basic statistics, count, mean, standard deviation, min, q1 or 25th percentile, median or 50th percentile, q3 or 75th percentile, max, all these things will get it. So now wherever you got little bit of doubt, you have to go and look at that lot size. If you look at it, there are 1883 observations. So every row there is a value filled, so there is no missing anywhere. The mean is around 1.339 e to the power of 4. Okay, so it is actually 1339 or 13,392 square feet is the mean. And if you look at the max is actually it is basically 1.2 lakhs of square feet. So it is big. So again, it is representing our histogram. Because of that, the problem is there. You can look at square feet. All properties square feet has been filled. That is why 1883 observations are there. Then mean is actually 2329 is the square footage of each property, and standard deviation is around 1336. Max is 8450. Not very unusual. Okay, so like that, you keep looking at it. Basement again, only 1657 observations are there. Okay, so a lot of places in the rows against the basement column, like your table is like this columns. So basement, okay, column, how is it there? This is my zeroth index, 1 2 3 1883 observations are there. These are all filled. Here some things are filled and some things are blank, some things are filled, some things are blank, and wherever it is filled, either it is 1.0 or it is nan. Okay, so but in spite of this nan 1.7, the only 1657 observations only are filled. Some 200 odd observations actually are left blank. So these are called missing. This is not good. We have to do something at the time of data cleaning to solve this problem. We have to fill this data with something. We cannot pass to our machine learning algorithms something with blanks. It will not accept also. Scikit-learn algorithm expects in every column some number only. Even your categoricals also have to be converted into numbers and passed to your machine learning algorithms. Machine learning algorithms are basically number crunching tools. So they need only numbers in tables, nothing else. Okay, no blanks, no descriptions. Okay, keep that in mind. So it looks like the basement feature only has the value 1.0. Why? Well, its standard deviation is also 0.0. So while its min and max are both 1.0. So basically we have to convert into 1010 kind of thing and fill all the columns here. Okay, so make a note. This is the important data cleaning activity we have to do. Okay, now once you look at the data, we have to keep asking some questions. So from looking at your data, what is the, because you have your data in front of you, tell me in your data set what is the earliest transaction year. Earliest transaction year means for the column tx underscore year, we have to see the min value. What is the min value in your data? One of you can tell me.
Something like 5.19 standard deviation is.
Not, I'm not asking. I am asking in your data set, what is the earliest transaction year? So
So
transaction
1993, 1993.
1993 is the first one property that has been transacted. That is the min of the TX year, 1983. Okay. Then we have, is it 1983 only?
Sir, 93.
93. Okay, then I got it wrong. Anyway, I will also go to my data sheet then, because I cannot scroll here, but I will go to my IPYNBL file and check it also. Okay, it is 1993. Okay, among all properties in your data set, what is the maximum number of bedrooms? So what you have to see? You have to see for bed column max value. What is that in your table?
5.0.
5. Yeah, okay. Then in your data set, do we see more variance in the number of bedrooms or the number of bathrooms? So what statistic you will see? So my question is, there is a column called bed, there is column called bath. Okay, some values are filled, 1883 values. Okay, so where the variation is higher, in bed column or bath column? Okay, what will you see here? You will see standard
Standard
deviation number for
deviation.
bed, standard deviation for bath. Whichever is having more, that is having more variance. That is how we answer that question. So in our data set, bedrooms with standard deviation of 1.069 sees more variance than bathrooms. So typically bathrooms in however big house, okay, there will be more bedrooms but there will be not too many bathrooms. Maximum bathrooms may be around 4. So minimum bathroom may be 1 to 4. But in a very big house, the bedroom can be minimum can be 3, maximum can be some 7, 8. So that is why the variation is like that. So we have to look at standard deviation to tell that. Now, half of all properties in data set have total floor size, that is our square foot, okay, between 1345 square feet and which other value. So there is a 25th percentile for square feet, there is 50th percentile, that is our median for square feet, and there is 75th percentile for our square feet. The interquartile range is between Q1 and Q3. Okay, so between Q1 and Q3, 50% of observations are there. That's what we are telling. Half of all the properties in the data set have total floor size between 1345 is our 25th percentile for square feet, and which other value. So we have to look at Q3 value. What is the Q3 value you are seeing in your data for square feet? What is the Q3 value you are seeing per square feet? That is 75th percentile. Yeah, 75th percentile for square feet is 3005. So between this square footage and the Q1 1345, 50% of the properties will be there. That is the interquartile range we are talking. So that is how, after looking at, we have to look for problems. You are trying to know about your data in this whole process. So it is not just making some pandas instruction work and feel happy. You have to now understand statistics, question some visualizations, try to get more insight into the data, and try to think about any potential problems in the data, because as I told you, better data beats fancier algorithms. So this is a very important activity. Okay, so we have done this step now of exploring basic information. Already we have done. First step is over. Okay, second step right now we have completed, that is we have explored distributions that are existing amongst numeric features. Now the third step we have to do, where we have to do our distributions of categorical features. Okay, that is what let us do now. So coming back to the index, we are in the first step of our project, and the first step of the project we have divided into 5 steps. Keep remembering these things. So we have done already 2. Now I am going and doing my third step, that is distributions of categorical features. So again we'll use visualizations as well as statistics and try to understand and make notes for any potential data cleaning or potential feature engineering activities that we'll do as our process. Okay, so we will be doing this now. So when we look at distributions against across categorical features, this kind of visualization will use. Histograms are not useful here. These are called count plots, okay, or bar graphs. Okay, here on the y-axis I am putting my exterior walls. There is a column called exterior walls. Okay, this is a categorical features. Okay, and this doesn't have any number in this. It has one of these 16 descriptions. Let's say this is 1 2 3, my index 50 100 1000 1883 observations are there. For exterior walls column, it is not filled with numbers. It is filled with, say, wood sliding. This is a description. Okay, or somewhere it is written as, like, let's say this is also wood sliding. This is also wood sliding. 50th one is brick. Okay, then brick, brick, brick. Somewhere here block. One of the descriptions, and like that, all descriptions. If you count unique descriptions, there are 16 unique descriptions for my exterior walls. Okay, and they are filled in this 1883 based on the house exterior wall type basically. Okay, so there are 16. So basically whenever you look at categorical features, this is a categorical feature, exterior walls. and the descriptions, each of them are called classes. Classes are in categorical features. So how many unique classes are there? How many unique descriptions are there? 16 unique descriptions are there for my exterior walls. Again, when you look at this graph, you have to think about few things. What is the most frequently occurring class? So if you look at it, brick type of exterior wall, most of my properties, almost uh, close to 700 properties out of 1883 have brick walls. Then actually aluminum vinyl siding is actually around 500. Then metal next, like that I can understand what is the most frequently occurring class. That is brick. So anything that frequently occurs in this categorical feature, the statistical term is it is a mode. Okay, frequency. Then what we have to see, are there any redundant classes? Whenever you feel this kind of columns, lot of times people do lot of mistakes. Okay, they don't properly fill that value. Because of that also, a lot of redundancy will happen. Okay, so if you look at here, concrete block and concrete, maybe they are one and the same. Some people typed it as concrete block, some people have put it as concrete. So they have become two unique classes, but maybe they are one class only. Or if you carefully look at it, there is a brick, okay, or wood, let us say wood siding, wood shingle, okay, then anything related to wood, maybe we don't know, maybe they are all same. So whenever you look at these kind of plots, look at these unique classes very carefully, and when you look at these unique classes very carefully, you will look for some redundant classes. Okay, that is one thing you have to look in categorical features. Then I think Ram Shankar asked about sparse classes. What is the meaning of sparse classes? Actually, though there are 16 unique classes, if you go back and see the column, some of these things, concrete, block, masonry, out of 1883, only one place it is there. Okay, those things are called sparse. Though there is a description, that is not very prevalent in the data. The prevalent classes are brick, siding, metal, combination. These are the more prevalent classes, more frequency they have amongst the 1883 observations or 18 that old properties. Okay, whereas wood shingle, masonry, asbestos shingle, rock stone, these are having less than 5 observations only filled with that class. They are called sparse classes. Look for them, because sparse classes are not good for your machine learning. They may overfit unnecessarily your model because too many features will happen. We'll see what happens later. How do we deal with these categorical features? But sparse classes are not good. So you have to figure out a way to combine them into whatever reasonably same class. Okay. So did you get what is sparse class? I think Ram Shankar has
Yes,
asked this question.
yes, sir. Sparse relates to frequency and outliers relate to variance.
Variance, yes. Okay. Okay. So now, alongside this bar graphs or count plots, we can look at describe. Only thing is that our describe function by default works with all the numerical features and calculates. So we already learned when we did the pandas, if you have to do for categorical features, you have to describe, but you have to pass an argument include equal to df dot object type. Okay, that is what I'm doing here. You also please do it. Okay, df dot describe argument is include equal to pass object. In fact, you can do like this object or directly object, it works, but index with an index operator you do this. So it through different kind of metrics, because they are not numerical columns, these are descriptive categorical columns. You got this table as an output. Tell me when you got it.
Yes, sir, got it.
Got it? Okay. So basically, what does it mean? We have three object types. One is property underscore type, has some descriptions. Exterior underscore walls has descriptions filled inside that cells. Roof also descriptions. So what are the metrics here? Count, unique, top, frequency. So here we can see the number of unique classes for each feature. So for property type, we have two unique classes. There are two types of property recorded in our data set. There are 16 unique values are stored in the exterior underscore walls column. And similarly, for roof also 16 unique classes are there. That is the meaning. Okay. For example, there are 16 unique classes for exterior walls, and the most frequent is the mode is actually brick. We have seen in our count plot. Okay, brick wall is the having some 700 observations. Okay, that is the most frequent. If you look at from a property type, only two unique values are there. The most frequent, the mode of the type of house is single family. Here it is composition shingle roof type. And if you look at the frequency of the top class is 1080, meaning 1080 observations have single family property types. And if you look at here, 687 are exterior walls have brick class, and here 1179 have this. Again, if you look at here the count part, what does it mean? The property type has 883 observations, means it's filled in every column, every row, whereas exterior walls are filled only 1660 times. So there are close to 200 places nothing is filled, they are left blank. Similarly, roof also only 1529 places only it is filled with one of these 16 values, otherwise it is not filled with any value. That is the meaning of this. So we have to look at all these issues. You have to make notes. Yes, there is missing data. At the time of data cleaning, I have to take care of it now. Okay. So there are whichever column, whatever is the issue, you are making notes now as you are trying to do your exploratory analysis. So right now we are exploring distributions amongst our categorical features in our data set and trying to learn. Okay, so we can use Seaborn's count plot function, very useful function to do, like you did histogram directly with pyplotlib, but you can do with SNS. Some method called dot count plot is there. So SNS dot count plot. How do we use it? Whatever on Y, I have to give the column name. I want to give exterior walls column. Okay, I am giving exterior walls column to my Y. You have to type it correctly. Whatever way the column is there in your table, that only you have to do that. If you type mistake, it will not work. So don't worry. Whenever something doesn't work, you see, am I rightly using the spelling of the column name or not? Then on the second argument, what I'm doing, I'm telling the count plot function that pick the data from df. My df is my table. So my table is df, and in that pick y column, and for y column I want you to draw a count plot. So what it does, on the x-axis it does the count, how many observations it found, and on the y-axis for this column what are the unique classes. For each class it will calculate the number, sum of those observations, and puts the count plot. That is what happens. Okay, so what we have done, when we get this graph, you have to ask this question. These classes are quite prevalent, which are brick is okay, quite prevalent, sliding aluminum vinyl is prevalent, bigger bars are there, metal is having sizable number, combination has sizable number. But actually most importantly, you have to look at for sparse classes. Some classes have really short bars, like your concrete block, wood shingle. They have very, very small bars. So these are called sparse classes. And we have to be careful with sparse classes. Sparse classes are classes in categorical features. So this is relevant to categorical features that have very small number of observations. They are called sparse classes. I'll repeat, sparse classes are classes in a categorical feature that have very small number of observations, like whatever we have seen. So they are little bit problem to our ML work. They tend to be problematic when we get to building models. In the best case, they don't influence the model at all. Okay, they don't cause any problem. But sometimes in a worst case, they can cause the model to be overfit. So we are fighting against overfitting, because overfitting or the whole model complexity issue is the big boss. It is the big villain for ML work. So we have to be careful with these sparse classes. So let us make a mental note to combine or reassign some of these classes later. So somehow take few sparse classes and put into one single class, then they will become more observations. Then your algorithm will treat them in a one way. Okay, that's why we will handle this in data cleaning step, and also we'll handle them in feature engineering step. So make a mental model around this, but only one property, one categorical feature only we analyzed. We can analyze all of them. So like in a typical table, in our table we have only 3 object types, so one by one we can do. But let's say you are dealing with some 200 column table where 25 these things are there, categorical features. So we can write a for loop to plot all of them as a single stroke. So what we are doing here, we are creating a for loop. A for loop has to get one iterable. As I told you, when you do df dot d types, okay, df dot d types is the attribute. When you check for it, what pandas throws out as an output, it throws out a series object. Okay, a series object. Series object is nothing but a column. Okay, a df, basically it is also a type of df. Okay, so what will be the column and what will be this? So what it does is that actually df dot d types, it will have an index column. Like in our all tables, index is a number, sequence number, whereas this column, the pandas series, when you do this df dot d types, it throws a column object which has an index and a value. Okay, index is nothing but your column names, like property type, whatever we gave, property type, tx price, okay, or year built, or let's say roof type. These are my indexes of the table, and value, what it fills, property type, it tells object because it is a categorical feature. Tx price, it tells float 64 or int 64, whatever is that. That is the type. Year built, int 64. Okay, roof type, object. So this creates a table like this. So this is a very important thing to know, because whenever you do DFD types, it throws an object about your table and gives this information. On the index, it gives the column names, and the values are nothing but its data type that it is stored with. So using that knowledge, what really we want to do here, I want to do a count plot for all indexes I want to put as a variable. I want to put these index as a list item. Okay, property type, whatever, comma, the second one, tx price. Hope you are understanding it. And next is year built. I will put a iterable like this, and I want to iterate through this, and where I will see the value is object. Okay, that is why I'm putting equal to object on the index. Okay, I'm putting a iterable, so it will only pick up my property type and roof type as my iterable. Okay, property type and these two will be there, so it iterates and plots my SNS count plot. When you run this, what it does 3 plots at a time. Okay, got it? So did you try this? So just I was explaining how it works. So don't think why this dot index and all, because we are creating an iterable using the pandas series object returned by df.d types. So in that I am filtering by object, and I am using the index because index is having my names of the columns, and I am iterating through those names of object types and doing my SNS count plot. Why I'm passing the first value, the feature, like that. If I have 30 crafts will be done. So try to use power of Python. Don't do inefficiently. That is the idea. Here only 3 are there. We can plot 3 different by typing 3 times, but you can use some programmatic cleverness as well. So did you do this? And did you get the 3 of them? Tell me.
No, sir, was listening.
Okay, just type this carefully and you will get it. Got it? Anybody who got it?
Yes, Madhu, got it.
Okay, so now once you get it, you have to carefully look at that. Okay, so anyway, property type only 2, and it is properly filled. There is no blank. Also, we have seen the descriptive things here. Exterior walls, roof again have 6. Then there are lot of what we call sparse classes. So we have to deal with this. Okay, here also there are a lot of sparse classes. We have to, again, one more thing you have to do is that a lot of times same thing will be typed again and again. So we will see. If you look at here, immediately if you see there is a composition type of roof with capital C, and there is something called composition with small c. Maybe they are same. Okay, these are all the things that we will have to very carefully look at it and make notes and clean them all at once. Okay, so with that we have covered these 2 things. We explored and went to our 3rd step. Okay, so maybe I will very quickly take you through the PD, though for those who have not are not coding. So anyway, this is our header. Okay, I ran them. Then we are reading our data CSV. Okay, then in the last session we looked at DFD types. Okay, when you do DFD types, it throws a table or a pandas series object. We want to do type check on that df.d types. Okay, this will be nothing but pandas.core.series.series. So it is a series type of object. So whatever we can do, we can do. Okay, so again we have seen the head of the table, tail of the table, few and in some occasions when you are dealing with large table, complex table, like whatever we have done toy underscore df while we are doing pandas exercise, that we concatenated with top 10, lower 10, and built a mini data frame so that we want to understand the data much better. Those kind of things you can do always. Pandas is there with you. Okay, then we have checked for all the columns, all those things, and again we have 3 categorical features we told. Then we use the for loop get the index, just to showcase to you last time. Then again, you can see what are the int 64 columns, all that you can do. So we did that. Now today we are doing numeric distributions. So visualizations, the good visualization that we use is histogram. Okay, df dot hist. So when you give, it will create all numerical features. Histogram, it doesn't look good. Okay, so we have some arguments that we can control and improve the visualization. So we are doing fixed size equal to 14 comma 14, x rot equal to minus 45. Then a little bit better things came. Then maybe take pause it some time, look at these things, anything surprising. Then you can do some more detailed histograms only for that column to understand it better. That is what we did today. Then visualizations alongside the statistics is very important. So we have did df.describe, then it looks at all the numerical features, and then we take a pause here and closely look at it. Okay, so count, how is it? Basement has only 1657, whereas the table has 1883. So a lot of missing information in basement. Okay, like that you will look at everything. Okay, rest of the columns all 1883, so it's decent. Then basement, again nothing is changing, metrics, all metrics are one or same thing. That is the problem. And in the histogram I saw a little bit of issue with my lot size. So I will go here and look at it. What is that? What is the mean of that 1.33? What is the max of that very big number? Okay, you make a note. Like that you will go and understand one by one without wasting lot of time. That is very important. As I told you, we can waste lot of time, do lot of pictures, but achieve nothing. But that should not be our goal. We have to do smart activity fast and try to understand the data. That is very, very important. That is why this template we are making it. So now, having done that and understood and made some notes about that, we will now only explore on our categorical features. So categorical features, we have to run df.describe by a different argument. And then when I did, because they are categorical, different kind of statistics are thrown. We looked at all these things now. Okay, here if you look at it, exterior walls and roof also have fewer observations than the table rows. So there is a missing information, and there are 16 unique classes. Okay, then we understood the mode of this data, all that. Okay, then yes, once we have looked at the statistically, let me also look at from the point of view of visualization. So very useful tool is that our count plot. How to use count plot? Just remember that. Why? We have to give the column name, and next argument you have to pass your data frame from where you want to pick up that values for that column, and then it calculates and does this graph for you. Okay, then we have to look for sparse classes that we did, and then using our little bit of knowledge of pandas series object, use the index as an iterable for object type, and we are in one single for loop. We are building all three count plots, and we look at it carefully alongside the numerical information and make notes. That is how we explore our data sets in a very systematic way, and that is a good capability for any good data scientist who will help in building ML models. Okay, so any questions? Any questions?
Sir, can we label the axis for histograms?
Can we label the axis right now? What is it coming there? Is it coming
Sir,
or not?
there's no label. There's no label. Only
No,
the
column
scale is
name.
coming.
I think column name will come on top. Let us see here. So the column name, active life. So this histogram is for active life. Okay, and in the bins, it is adjusting the bins based on the numerical data. Okay, like square foot. Let us look at where is the square foot active life basement baths. Let us see, or So it is already picking up by some basic arguments from the column name, and it automatically, again, you can adjust your bin size. You can tell that min bin size is this, like that. You can do those things. If you read this documentation, you will find that. Okay, a lot of things can be done. Okay.
Yes. Yeah. Thank you.
Okay. Yeah. If you are interested, go through the documentation. But again, no need to waste a lot of time. For academic purposes, we can learn that. Okay. Any other questions? If there are no more questions, so let us stop here. See you day after tomorrow. And bye bye, everyone. Learn, have fun.